Hello everyone, thank you so much for joining us today. I hope everyone's doing well and staying safe out there. My name is Victoria and I'm a Senior Business Development Coordinator at 2H Offshore. With many industry events and conferences canceled due to COVID-19, we've put together this series of live webinars to keep our valued clients and colleagues up to date on the latest happenings in the world of riser and conductor engineering. I want to welcome you all today to our webinar entitled Stream JIP, SCR, and SLWR Field Data Learnings. Before we get started, I'd like to cover a few important housekeeping items. Firstly, this webinar is being recorded and it will be made available to you soon, so please look out for a link to that in your email. Secondly, if you have technical or content-related questions today, please feel free to ask them at any time. You can use the Q&A box that is located on the right-hand side of your screen. At the end of the presentation, we will go through as many questions as we can, but if you have further questions, feel free to contact our speaker directly after the presentation. And with that, I'm very happy to introduce our speaker today, Deanne Decker. Deanne has over 14 years of experience in subsea design, integrity management, and life extension projects. He's based in 2H's Houston office, where he leads multiple engineering projects as well as technology development programs such as the Stream and Tracks JIPs. Deanne has authored and co-authored several conference publications and technical editorials. Deanne holds a Master of Science degree in Mechanical Engineering from Ohio State University. And with that, I'll pass things over to Deanne to get us started.
Thank you, Victoria, for the warm introduction. I am excited to be here today speaking on this topic, and I hope you will all find the information useful. So the outline of my presentation today is to give you an introduction to what motivated us to start this JIP. Then I talk briefly about the JIP participants and the objectives, the short-term objectives. Then I talk about the field data sets that are the backbone of this JIP. Then we have compared our analysis results to the field data sets for both wave-induced fatigue and VIV fatigue, and I talk about that. And finally, whatever I have talked about in terms of results today is phase 1, which is over. And then I talk about the phase 2, which is going to start end of this year or early next year. And finally, a summary of whatever I said in the presentation. So SCRs, they are everywhere in the deep water world, and SCRs are really reliable. They are widely used, and they are a simpler design than the other risers. They are very versatile. You can attach them with semis, spars, TLPs, and FPSOs, and so a lot of good things about SCRs. And on the left here, I show you a simple SCR, a steel catenary riser. On the right side, I show you a lazy wave version of it, which we refer to as the steel lazy wave riser, SLWR. Now, throughout the presentation, when I say SCR, I typically mean both the SCR and the SLWR. So, so bear with me on that. Okay, so SCRs are great, but SCRs can also drive your project costs if you're not careful. SCR fatigue is typically the driver of these fatigue costs. And because of our analysis methods, the way we analyze the design conservatives we use, sometimes we can end up with costly solutions such as cladding, for example, that is going to add millions of dollars to the project, upset ends, superior welding, and then counter boring, etc. Or is it even the lazy wave implementation of it, the SLWR, is a cost item. Then sometimes your vessel might be dictated by your riser, at least partly. So a lot of items where we can increase our costs. And not just in new design, but also in life extension of SCRs. A lot of SCRs in the Gulf of Mexico are coming to the end of their lives, which is typically about 20 years. And soon we're going to have to think about life extension. And we are thinking about life extension because the wells keep producing newer tiebacks, etc. And if you use our traditional design methods, you may not be able to get the life extension. So there is a motivation to look at SCR fatigue. This is why we started the SCR fatigue JIP. And what is the best way to benchmark our analysis models? That is through measured data. We know that 9 SCRs have been monitored around the globe. So can we use this field data to refine our design methods? That was the big question. And that's how we started Stream JIP sometime in 2018, beginning of 2018, I believe. The members are shown on the left side. You can see Shell, BP, Anadarko, Chevron, and ExxonMobil. STREAM stands for Steel Riser Enhanced Analytics Using Measurements. So the word measurements is key here. We're using measured data and we are improving our understanding of riser response. The last bullet point here shows what we are after. We are after unknown unknowns, stuff that we do not know about at all. We discovered something called high frequency response. I'll show you in a few slides. Then there are unknown knowns, stuff that we know exists, but we haven't got a lot of evidence about. So we want to learn about those. For example, heave-induced VIV. And then the known unknowns, basically items that we know we don't know enough about. We want to calibrate that. For example, strict hydrodynamics. So with that, let me show you all the field data sets that we used in phase one. So here you can see 5 risers. 4 of them, the first 4 are SCRs and the last one is an SLWR. They are either attached to TLPs or SPARs. There are varied levels of VIV suppression on these risers, and you can see the top 3 are partially suppressed by VIV, and riser 4 and riser 5 are almost nearly fully suppressed for VIV, except for the lazy wave where the buoyancy part is not suppressed. That's kind of important because this leads to increased damping. They are in water depths ranging from 3,000 feet to 5,000 feet. These are approximate. And then the monitoring system. If you look at the picture on the right, you can see a cluster of loggers at the hangoff and a cluster of loggers at the touchdown zone. That is how they are typically monitored. And we have a riser hangoff column and a riser TDZ column. And then sometimes we have loggers on the vessels as well. And you can see that these risers all have different levels of monitoring. So let's look at the data of each one of these risers in a little bit more detail. On the left side, you can see a picture of riser 1 attached to a TLP, and the yellow blocks here, they represent the monitoring systems. You can see that there are quite a few monitoring systems up at the top, both on the riser hangoff, riser porch, and the TLP, and then 3 loggers near the touchdown zone. And again, the data that we got from this is great. We did not see any hurricanes. We saw a maximum HS of 13 feet. Unfortunately, the wave data was not available for a lot of the times, but from what is available, it was 13 feet maximum. Current speeds, well, we got the max current speed of 1.6 knots. It didn't cross the 2 knots barrier. And the response characterization, when we looked at the response of the riser, we saw that 65% of the time it was purely wave driven response. And 31% of the time there was wave and VIV as well. And we know that by looking at spectral plots. And I'll show you in a little bit. So riser 1 field response. On the left, you can see a timeline of the acceleration, RMS acceleration from one of the touchdown zone loggers. And you can see embedded on it is the HS, the wave height, the scale for which is on the right side in feet. And the wave height, as I said, was not available for a lot of the data. But for whatever it was available, you can see that there is a good correlation. And that is something that we have seen for all risers. And on the right, I am showing you a spectral plot for one of the logging periods. It's about a 15-minute period from, it's a spot on the curve on the left side. And here I am showing you the frequency content of acceleration. You can see the vessel logger, which is the blue one, and a touchdown zone logger, which is the red one. And you can see the damping. That's what we are after. Our analysis models predicting this damping well or not, or what do we need to do to predict this hydrodynamic damping. Now, this is a plot where I'm showing you all the loggers from the bottom up to the top. And you can see the little X over Ls. They are sort of starting at zero from the touchdown zone and going up. And you can see that the bottom three loggers are touchdown zone loggers, and the rest are near the riser top or at the vessel. And you can see the wave activity in the top loggers, but it has died down towards the touchdown zone. Also, another phenomenon we see is the TLP, the heave natural period at 3.8 seconds. It is our loggers are very sensitive and they capture that as well. So yeah, the question is, how does this compare to analysis results? Riser 2 is also a TLP riser, and it is partially faired, and it does not have a lot of instrumentation, just two loggers. However, it has a lot of good data. We got two hurricanes, Ike and Gustav, passing through it, and HS up to 43 feet, like a 100-year hurricane almost, were observed. Kind speed was also higher compared to Riser 1. We saw a max speed of 2.6 knots. And when we did the response characterization, we saw that, I mean, there was wave activity throughout, and 70% of the time, approximately 70% of the time, we saw VIV happening as well. So I'm showing you here on the left again a similar plot as for Riser 1. It's an acceleration time trace from one of the touchdown zone loggers. And you can see the two spikes for the two giant hurricanes, Gustav and Ike. And so it's a really great data set. Again, you can see the excellent correlation between wave and the riser acceleration. We did not observe good correlation with the current on any of the risers, and hence I'm not showing you a current versus acceleration plot. So as I said, we observed VIV. Well, I'm not showing you a normal VIV here. On the right side, you can see something that is called higher harmonic VIV, where you can see a lot of peaks, and each peak is a multiple of the fundamental cross-flow peak at 0.17 hertz. So 0.17 hertz is the cross-flow peak, 0.35 hertz is the inline, and 0.53 hertz is the next cross-flow, zero point 0.7 is the next inline, and so forth. So this higher harmonic VIV is not usually modeled. It is nowadays modeled in SHARE 7, but it's very conservative. And we did not see it happening all the time. It happens rarely. So something that we learned about, and we can calibrate our models to this. And interesting response here, right after Hurricane Gustav and before the start of Ike, we saw something that is high frequency and high response of the riser. And you can see the spectral plot on the left, and this frequency is higher than the usual wave and VIV frequencies. And the amplitudes are also not small. And on the right side, I'm showing you the so-called waterfall plot, which is just a time varying FFT, basically multiple frequency plots stitched together, the frequency plot being on the left. And it is showing the same response, basically, almost a very consistent response at 0.8 hertz. And this is something that we did not expect. It is what is called the unknown unknown. That is something we did not expect and we did not know about, and we came to observe it. It could be hurricane-induced currents causing VIV, but we will go into detail in phase 2 on this particular response. Riser 3 is another TLP riser, and you can see there is a cluster of loggers at the top, cluster of loggers at the bottom, and it is in about 3,000 feet. This data is more like riser 1 data. We did not see hurricanes. The max HS was 10 feet, max current speed was 1.6 knots. When we did the response characterization, we saw that about 50% of the time it was pure wave, 35% of the time it was combined wave and VIV, and we observed this heave-induced VIV about 6% of the time. That is something that we know exists, but we typically do not use it in design. And if we observed it for a TLP, you can imagine it does exist for semis or FPSOs. Again, I'm showing you the field response. On the left, you can see acceleration versus wave height, and you can see there's a good correlation. And again, on the right side, I'm showing you something like riser 1, comparison of a hang-off logger to the touchdown zone logger, which is in green, and the damping is quite evident. Here I am showing you all the loggers. On the left side, you can see the spectral plot. The bottom three spectral plots are for touchdown zone loggers. The rest are for hang-off loggers, and the very top one is for the vessel logger, X over L of 1. And here I'm showing you a VIV response, a multi-mode VIV response. So multiple modes occurring at the same time or occurring one after the other. In the waterfall plot on the right side, you can see these same frequencies. They are switching between each other. Let's say at about 0 to 300 seconds, they are in a particular frequency. Then they shift a little bit. They are at another frequency. Then they shift again at 600 seconds. They are at another frequency. This is the mode time sharing that is being modeled in Share 7. So since version 4.5. So Share 7 is doing a good job of that. And you can see that this is VIV because it's not on the vessel on the top logger. So that was riser 3. Now I'm going to talk about riser 4, which is a spar riser. It is fully strict. It is very well instrumented. It has got a lot of loggers at the top, even more loggers at the bottom, both motion and strain loggers. And the data was more like riser 2, I would say. We observed one hurricane that was about 25 feet high. We observed current speeds up to 2.5 knots. And when we looked at the data, we found out that there was almost no VIV, a testament to the strakes functioning as intended, and no VIV even in 2.5 knots. Again, this is an acceleration timeline plot versus wave height, and it is a pretty good correlation. Considering the risers are hung off at a depth below the spar, so it's the spar motions that are driving the riser response. Next is riser 5, which is last but not least. This is a lazy wave riser, and it is almost entirely covered by strakes or fairings, except for the buoyancy section, which is not suppressed. And the data we got is the HSS were almost day to day, except for Hurricane Isaac, where it went up to 18 feet. Max current speed was observed to be 2.1 knots. Now, when I say max current speed for any of these risers, it is what we have measured. There could be a higher current speed above the measurement point, for example. And we saw that the response was almost all wave dominated. There was no VIV, even though the buoyancy section was not straked or fair. And we saw that since this is a lazy wave riser, it isolates the motions from the top to the touchdown zone. So touchdown zone logger response was practically nothing. It was in the noise region. So here I'm showing you on the left a hang-off logger, which is the red timeline, acceleration timeline, compared to the significant wave height in red. And you can see Hurricane Isaac there and an excellent correlation. Now let me show you the touchdown zone logger as well. And that's the green line here. And you can see that there is barely any response, which again shows you that the lazy wave shape works and it isolates the motion as intended. On the right, I show you the spectral plot for all the loggers on the system. The bottom five are touchdown zone loggers and the rest are hang off. And you can see the wave dominant motion practically dies out at the TDP. And this was during the peak of the hurricane, by the way. So it didn't do anything to the touchdown zone. And also you can see the spar low frequency motions here, the pitch and the drift that's being reflected on the riser. So that was all the data sets. Now let me show you what we have done with the data sets. So here again, let's say these two little rectangles are the logger clusters. So you get the field data, you QA the data, make sure that there is no, spikes or unfunctioning loggers being included. You screen the data, you look at the spectral plots, identify if it is VIV or wave or anything else. Then for the VIV and wave events only, not the heave-induced VIV or any other response, we calculated the fatigue, which is the data analysis part of it. Next, we need to benchmark our analysis model. So what we did was we used a FlexCom model. We could have used OrcaFlex. I'm assuming it'll be very similar. And we used the displacement load of one of the hang-off loggers, and we used it to drive the model. We used typical industry standard parameters. For example, we don't use structural damping. We use, strake CD of 2.0, for example. And we would find out the response at the bottom at the location of the TTZ logger, and we'd compare that with whatever we have measured from the actual TTZ logger. And we would then calibrate our parameters, the parameters that we think can be played upon or should be played upon, and we try to match the response better. We also develop some factors of safety in this study. And for the wave events, it's very similar, except that you build a model in FlexCom and Shear 7. We use Shear 7 4.9. And the load here is not a displacement load. It is a frequency domain analysis. So we use the measured currents. And again, we compare it to the touchdown zone logger response that is actually measured. For Shear 7, I should tell you that we have not done any calibration. We have just compared. So what parameters can we play upon? First of all, like I said, we have only included wave and VIV events. We have not included any of the other items like heave-induced VIV, VIM, etc. We are looking at parameters that we know are conservatively used. For example, strake hydrodynamic coefficients, structural damping, and background currents. The background currents are there, but we rarely use them in design to be conservative. VIV fatigue, like I said, no calibration, just a comparison with the default Shear 7 parameters. Except we haven't used a higher harmonic function, which makes it really conservative. So this is the result for wave fatigue. And as you can see here, this is a plot of the analysis fatigue damage versus measured fatigue. This is for all the risers, all for 5 risers. And you can see that with the typical design parameters that I've shown here, you are over predicting the measured fatigue. So you're conservative. That's a good thing. In an ideal world, you're going to lie on the gray line where measured would be equal to analysis. So now we used a higher strake CD, higher fairing CD, we use background currents, we use structural damping, and we got the blue data points here, which is much closer to the line. We call this the best fit parameters. And very important thing is the scatter is less. It's more reliable prediction right now. So what we have proved in this JIP is that typical design parameters are unambiguously conservative. There's no doubt about that. And there is a factor of 3 improvement when we go from the red data points to the blue data points. And there is less scatter as well. And I will again remind you that this is for all risers. This is consistent. So let's say we know that the design parameters are on an average factor of 3 conservative, you have a factor of 10 safety factor, so you're being 30 times conservative, just to put in perspective. And we came up with a set of recommended parameters for the participants to use from this JIP. VIV comparisons. The plot on the left shows one of the events. I think I showed you a similar plot some time ago for Riser 3. This is just showing you a multi-mode event. And on the right, you can see VIV excitation frequencies versus event number. The event number is just a discrete logging period of 15 minutes. And you can see in blue the measured VIV peak frequencies. So, and Shear 7 predictions are put in red, and you can see that they are not very far off. Shear 7 does a good job actually. It is only slightly over predicted compared to the measured in terms of frequency. Again, very easy to calibrate, but we haven't done so in phase 1. We're going to do it in phase 2. Let's look at fatigue damage. So a similar plot as I showed for wave, measured versus shear 7, and you can see that shear 7 is conservative by a factor of 2 near the TDP. However, there is a lot of scatter. Basically, shear 7 is very sensitive to the input current data, and that's why we think there is a need to calibrate it. And also, some of you may have seen the drilling riser plots where we show that the shear 7 results are like 30 times or 10 times more conservative. And we did not observe that for the SCRs. It is a factor of 2 conservative. So that was phase 1. That's all the results for phase 1. And we are going to start phase 2 later this year or early 2021. And what are we going to do? It is shown on the left. We're going to have an additional data set, at least one additional, which will be an FPSO SCR, so high heave response. Then we're gonna look at the heave-induced VIV in greater detail. We have the data, so we want to see what triggers it, how much fatigue damage it imparts, etc. Then we can look at the hurricane data. By the way, whatever calibrations and benchmarkings we have done, that is for day-to-day sea states, which is more relevant for fatigue. We haven't looked at the hurricane data yet, the Ike and Gustav data. So we're gonna look at that in phase 2. Shear 7 calibration, like I mentioned before. Then also we're going to do VIV probability of occurrence. So basically, whenever you give a current to shear 7, if it satisfies the Struhel formula, it's going to give you a fatigue damage. It's a software. But in reality, sometimes VIV doesn't occur even if the currents are high enough to cause VIV as per the Struhel equation. So that is something we want to explore. Can we quantify this VIV probability of occurrence and use it in our calculations? Then we want to look at combined VIV and wave events. This is something that the operators were very interested in. Basically, when nowadays when we do fatigue, we look at VIV fatigue separately, we look at wave fatigue separately, and add the fatigue damages from the two. In reality, they are occurring together, and the stress ranges need to be added together to get the final fatigue damage. So we have the data to look at such events, and we plan to do so. And also there might be some damping on VIV, for example, from wave, and that is what we are going to look at. And finally, there is a lot of unused data from phase 1 because of budget and time constraints. We could not look at all the data from phase 1. I would say we looked at about 30% of the data actually. So there is a lot more data that we can add to further validate our parameters in phase 2. So phase two, same participants, except there'd be some additional participants, uh, Saipem and probably Petrobras, and we are open to additional participation. More participants, less is the fees, basically. So, summary of what I said so far. Uh, Most importantly, Stream JIP has demonstrated opportunities to improve our modeling methods. We are conservative by a factor of 3 when we compare to measured data. Shear 7 is conservative by a factor of 2, but there's a lot of uncertainty in the predictions because of the sensitiveness of Shear 7. We observed higher harmonic VIV, although rarely. We observed heave-induced VIV, for example, for about 6% of the time for riser 3. And we know that it exists in the FPSO data set that we are going to look at in phase 2. And so phase 2 is going to look at FPSO data set, hurricane events, heave-induced VIV, VIV calibration, including the higher harmonic events, probability of occurrence of VIV, combined wave and VIV events, and unused phase 1 data. And I believe that's all I had, and I'm going to hand it over to Victoria. Thank you.
Thank you so much, Deanne. We've had some great questions, so I'll go ahead and get started asking those. First question was, did you do any study on the seabed effects on the riser response?
Yeah, that's a good question. Seabed effects is another layer of uncertainty, and for this phase, at least, we try to stay clear of it. Because we need the instrumentation. We need enough strain loggers at the bottom, placed closely to really study the effect of soil. So whenever I say test down zone loggers, I'm talking about a logger that is about 100 feet from the nominal touchdown, so that we are steering clear of seabed effects.
Okay, great. Next question was, which values of damping have you used for the SCRs?
We used the 0.3% structural damping. We used it just on the stiffness matrix only. So we are being quite conservative, actually, even when using it.
Okay, great. Next question was someone who came in a little late. It might have been at the start. They missed which TLP you were talking about. Did you mention it?
No, actually, it's confidential information, so we are not giving out the names of the TLPs.
Okay. Next question is, have the enhanced wave fatigue parameters been used on an actual project?
Yes, anecdotally, what we have heard is that some of our participants have used these recommended parameters, and both in new designs as well as life extension studies. And really, that's something that we are happy that we have contributed to the industry.
Next question is it necessary to donate data to join the JIP?
Oh no, yeah. If you have data and if you give it, that'll be great. But if you do not, you can just join as without the data. And we had participants in phase 1 that both donated data and did not donate data. So the same will be for phase 2 as well.
Okay, that's good to know. The next question is, how would you expect a flexible riser to perform? Could we assume the similar performance characteristics?
Yes, good question again. The this is we are saying that these parameters work for SCRs only right now because it'll be going beyond our. Uh, I guess it is too early to say that it's gonna work on flexibles as well. Uh, but there'll definitely be more damping, and there are no strakes usually on flexible risers. So the entire strake CD concept is kind of moot here. But if there are background currents and you are confident of a particular value, it is recommended to be used.
Okay. Next question. Have you considered comparing the measured VIV data to time domain VIV analysis?
Yeah, we plan to do so in phase two again. We are going to look at some time domain as well as frequency domain, most likely in Orcaflex, the wake oscillator model. We're going to see how it performs when compared to measured data.
Okay. This also might be confidential, but where would they get more information on the loggers?
On the loggers, I mean, the specific loggers that were used for these data sets, I suppose I'm not allowed to reveal, but most of these were Pulse loggers. And if you go to the Pulse website, Pulse being our sister company, then you can find out some information on the typical loggers. The loggers are actually updated nowadays. It has atomic clocks and that kind of, extra Gizmo, I suppose.
Okay, and next question. It was from the start. What was the profile current?
Uh, well, we used current profiles. If so, typically the current profile would be shared. I hope I'm answering that question here. And during loop events, they're definitely be very shared. And during day-to-day C states, I would say they are less shared, more uniform type, but still very shared, I would say. Compared to, let's say, other places in the globe.
Okay, and you might have mentioned this, but has this data been used to successfully support Rise of Life extension yet?
We again, I have heard anecdotally that these parameter sets have been used in a project, uh, life extension project as well. Again, anecdotal information.
Okay, I think we have time for one more. The last question is, are loggers always installed on the risers right from the initial installation?
Yeah, we would love for loggers to be installed on many risers, but that's something that is not very common. And as I've said in one of the slides, beginning slides, there have been only 9 SCRs that have been monitored actually. So no, loggers are not installed on all risers as a given. It's rather rare, I'd say.
Okay. I think we did just get a couple more. I'm just going to squeeze one more in. Um, it is mentioned that higher CD values were used for the best fit data. How much would the CDs increase, and how do these numbers compare to the experiment/models?
Again, I cannot give you the exact CD value out of because of confidentiality reasons, but I can tell you that they compare very well to test data. And actually, MIT did a bunch of tests, and they saw that straight CD can be really high in low KC flow. And I would say that our assumptions were in line with MIT's experiments.
Okay, perfect. Well, thank you so much, Deanne, for all the information on the topic. That's about all the time we have for today. And as we mentioned earlier, if we didn't quite get to your question, or if you would like to continue the discussion, you can contact Deanne directly using the details provided here. If you can go to the next slide. And thank you all for our audience for your time and participation, and we hope you found it useful. And you'll join us for more webinars in this series happening every 2 weeks during our time at home. If you check out our website at 2hoffshore.com, there's more details for our next round of webinars, and you can sign up. And look out for a recording of the webinar in your email in the next 24 hours, and we hope you all enjoy the rest of your day. Thank you.
Thank you.